So let's go through the rules for balancing in acidic conditions, and we're going to use oxidation numbers to do that. So again, the redox species might be included in the reaction, but it might be missing some other things. And if it is in acidic conditions, the two things that it could be missing are water and hydrogen ions. So what we're going to do is we are going to add in water and hydrogen ions in order to complete the chemical reaction. We're going to add the waters first in order to get the number of oxygens to balance, and then we're going to add in hydrogen ions to get the hydrogens in the equation to balance. And again, by that point, once we have done that, all of the atoms should be balanced. And as a good way to check these to make sure they are balanced, you're never wondering whether you did the balanced equation correctly. As long as you can count, you can check your own balanced equations to make sure that they are balanced. And checking the charges is a good way to check because you're probably using the atoms while you're doing the question. So at the end, if you use the charges to check to see whether it's balanced, then you'll know you are correct. All right, so let's try balancing these using the oxidation numbers, and specifically in acidic conditions, which means we're probably going to have to add water and hydrogen ions in order to complete the reaction. And you can sort of see from this first one here, we are missing oxygens on the right. Like we have some oxygens on the left and there's nothing on the right that has oxygens at all. And it's because it's an incomplete redox reaction. So we're going to be adding water and hydrogen ions in order to fix that. First thing we want to do is we want to look at the oxidation numbers. So if we look at oxygen here, we know it's going to be -2, and there are 7 of them, so that's a -14. We know the sum is going to be -2, so essentially the chromium here has to come up with a +12 between the two of them, so each one must have an oxidation number of +6. Iron is an ion, so its oxidation number is its charge, and then that makes the right-hand side easy because chromium is going to be +3 and iron is going to be +3. So we know that the one whose oxidation number is going down is going to be going through reduction. So if we look at chromium, it starts off as 6 and it goes to 3. So we know that's reduction. And we have our oxygen, which isn't even on the right-hand side, so hopefully it's not doing anything. But our iron is going to be going from +2 to +3, which must mean it is losing electrons, it's losing negative charges, bringing its oxidation number up. So that is going to be our oxidation. So chromium's being reduced, iron is being oxidized. Now, in terms of number of electrons, if we look at our chromium, we're talking about 3 electrons, but there are 2 of them here. So what I will do is I'm going to put a 2 in front of this chromium so that I have 2 on both sides, and I'm going to apply that. So I'm talking about 6 electrons needed to do my reduction. My oxidation is just going to involve 1 electron to go from the +2 to the +3. It is just going to be losing that 1 electron, and there's only 1 of them, so we're good there. Now, in terms of factors, the lowest common multiple is going to be 6. So I'm going to multiply this by 1. I'm going to multiply this one by 6. And those factors should balance my redox species. So I'm going to now drop in my 6 in front of my irons and my 1 in front of my chromiums. Now this is a temporary coefficient. I'm going to multiply it by 1 so it becomes a permanent 2. And now I have my redox species balanced. What I then want to do is I want to add in some water on the, there's 7 oxygens on the left-hand side, so I'm going to add in 7 waters on the right-hand side in order to get those oxygens to balance. So now my oxygens are good. But the problem is when I add these 7 waters, they contain 14 hydrogens. So I'm going to have to over here, let's see if I can get some room here. Pretend you can't see that. I'm going to have to add in 14 hydrogen ions to the left-hand side. Now my atoms should be balanced, and I can check. I should check my atoms to make sure they're the same thing. I've got 14 hydrogens on both sides. I've got 2 chromiums on both sides. I've got 7 oxygens on both sides and 6 irons on both sides. So all the atoms are balanced. Then the next thing that I can do is I can double check that the charges are going to balance out. So adding up charges, on the right-hand side I have 14 positives and I have 1 negative, so I'm down to +12, just to keep track of this. Then I have +2 times 6 is going to be plus positive 12 again. So I have positive 24 as my charge on the right-hand side. On the left-hand side, I have my 2 chromium ions, so that's going to be positive 6, plus the 6 times 3, 18 positives from my irons, and so that's going to give me positive 24 on the right-hand side as well. So my check works out, 24 and 24. The atoms are balanced, the charges are balanced, everything's good. Next one, let's try this just as a double practice. Clear up some room here. Same thing, oxidation numbers, and again I'm going to ignore the oxygens, but what I will focus on is the chromium. So we've seen this guy before, so we know it's going to be positive 6. I'm going to ignore oxygen because I know it's not going to be my oxidation or reduction species. I have carbon here, and this is going to be plus 4. And this carbon here, I've got 4 at negative 2 each, and the sum is going to be negative 2, so that's going to be negative 8. So these are going to have to be positive 3, so they add up to be positive 6, and then the negative 8 will leave me a sum of negative 2. So I have my redox species, and again, we've got our chromium. It's going from 6 down to negative 3, sorry, positive 3, so it is going to be a reduction. Our carbon, let's see if we can fit this up here as well, is going through an oxidation, and it's going, oxidation is the loss of electrons, so by losing those negatives it is going up. In terms of electrons, we're talking 1 electron, but there are 2 of these, so we're really talking about 2 electrons. For our chromium, we're talking about 3 electrons, but again, there's 2 of them, so let's put a temporary coefficient of 2 in front of there. I forgot to do that for carbon. So temporary coefficient of 2 in front of there. So for the chromium, I'm talking 2 of them as well. So I'm going to multiply that by 2, and I will end up with 6 electrons for my chromium. And again, my lowest common multiple is 6. So my factor that I'm going to apply to my carbons is going to be 3. And the factor that I'm going to apply to my chromiums is going to be 1. So let's go ahead and put that 1 in front of my chromium. So this 2 becomes a permanent 2. And my 3 is going to go in front of my carbons, and this is now going to be 2 times 3 is going to be a 6. So my redox species are balanced. Now let's check our oxygens. On the left hand side we have 7 plus 12 is 19. On the right hand side we have 18, so we're going to have to add 1 over there, and that should give us our make sure I did that right there. Hold on. 6 is 12. No, that's not right. So we have 12 oxygens on the right, and what did we say on the left? 7 plus 12 is going to be 19, and so we have our 12, so we are going to need 7 of those on the right-hand side of waters to get the oxygens to balance. The hydrogens are now 14, so let's look at a little bit of deja vu here. 14 hydrogens on the right-hand side. Again, our questions in the way. There we go. Barely see it. So we have 14 hydrogens on the right, and now we want to check to make sure that works. If our atoms balance out, then we can check our charges, and they should also balance out. So on the right-hand side, let's get rid of the oxidation numbers so I can see this a bit better. On the right-hand side, I've got positive 14. Minus 2 is positive 12. Minus 12 is going to, sorry, minus 6 is going to be positive 6, I believe. On the right-hand side, the only thing I have with charges is going to be the chromium, and there's 2 of them. So the charge total on the right-hand side is positive 6, left-hand side. So my check works out. The atoms balance, the charges balance. I've got my balanced redox equation. All right, under basic conditions, it is the same idea, but so these same steps are the same as what happened under acidic conditions, but there's going to be one extra step. We are going to put in hydroxides in order to neutralize the hydrogen ions that would have been okay if we're under acidic conditions, but we're talking about basic conditions. So we're going to go through the same steps, which will probably give us some hydrogen ions that are there. And remember, these are positively charged hydrogen ions. But since it is basic, we are going to neutralize those using OH. So again, same thing. We're going to add water to balance. That's a 2. Water to balance the oxygens. We're going to add hydrogen, and then to neutralize the hydrogens, we are going to balance hydroxides. We're going to react these guys if they happen to be together. We'll react them and turn them into water, and then we want to make sure we cancel out any like terms between the left and the right-hand side. Okay, so same step. First, oxidation numbers. So we have 0, we have -1, we have 0. I'm going to ignore the hydrogen, and so here is oxygen at -2. And as we can see, this isn't a complete reaction. We're missing some things, so we're going to be adding those in under basic conditions. Our reduction should see a drop in its oxidation number. And so if we look at oxygen going from 0 to -2, that is, it is gaining 2 electrons, but there's 2 of them on the left-hand side, so I'm going to put a temporary coefficient of 2, so I have 2 on the right-hand side. And so I'm really talking about a reduction. It is gaining 4 electrons. And my oxidation should see a increase in its oxidation number. So we're going from -1 to 0. That is 1 electron being gained. But I see there's 2 iodines on the right, so I should put a temporary coefficient of 2 iodines on the left. I'm going to multiply that by 2. So really I'm talking about 2 electrons going through my oxidation. Lowest common multiple is 4. So I'm going to put a coefficient of 1 in front of my reduction species. I'm going to put a coefficient of 2 in front of my oxidation species. And let's do that. A 1 here, a 1 is going to be applied here, so that becomes a permanent 2 now, because 1 times 2 is 2. I'm going to put a 2 in front of my iodine, and 2 times 2 gives me 4 iodines here. So I have my redox species balanced. Now I want to make sure I follow the steps. I'm going to add water to balance the oxygens. But I've got 2 oxygens on the left, I've got 2 oxygens on the right, so they're already taken care of. So the next step should be to add hydrogen ions to balance the hydrogens in the equation. I have 4 of them here. I don't have any on the right-hand side. So I'm going to add 4 hydrogen ions on the left-hand side in order to balance those 4 that are in the water. Now, because if we were under acidic conditions, we'd be done. That'd be it. But since we're under basic conditions, we're going to add in an equal number of hydroxides to balance, neutralize those hydrogens. But if we add them to the left-hand side, it would throw off the balancing of our atoms. So we're also going to add the same number. We added 4 to the left. We're going to add the same number to the right-hand side. So 4 on both sides. Now, these 4 hydrogens and 4 hydroxides, they are going to neutralize and form 4 water molecules. So really, I have 4 water molecules on the left, and I have 2 on the right here. So really, we can simplify that. We can cancel out those 2 and change this 4 into a 2. So let's clean this up a bit. So those 2 waters, let's write them down here. 2H2O. And we should now have all of the atoms balanced, but again, as a check, we should check charges. So if we look at the left-hand side, let's check atoms too, just because that was a little bit much. So again, that water's gone. So on the left-hand side, we have 4 hydrogens. On the right-hand side, we have 4 hydrogens. On the left-hand side, we have 2 oxygens and 2 oxygens. That's 4. On the right-hand side, these waters are gone. So we have 4 oxygens, 4 on the left, 4 on the right. We're good. 4 iodines on the left, 4 iodines on the right. Perfect. So the atoms balance, and we can now check charges. Let's add them up separately. So here is -4 from the hydroxides. And if we look on the left-hand side, the only thing that has charges is the 4 iodines. So we have -4 on the left-hand side, -4 on the right-hand side. The charges balance. This is our balanced equation.